So to summarize section 1 of the course, fluids flow. A bit more to it than that. Fluids flow as a continuum set of fluid parcels. You can think about each one individually in Lagrangian sense, but because they're a continuum and they all interact with each other and there's no spaces between these fluid parcels, we also have to think about those interactions and how they form a velocity field. 3 components, u, v, w, 3 dimensions, x, y, z, steady or unsteady, t, and that's the Eulerian vector field, velocity field. We visualize fluid flow by streamlines. That's the tangent lines of the Eulerian velocity field. We can also think of path lines, which is Lagrangian tracking, which is an initial value problem where we integrate position and with respect to time with some initial position. Or by streak lines, which is a related sort of initial value problem, but it's the end position of all of the points that left one emission point over a period of time. Especially important, since we have a velocity field, steady flows, those that don't change in time, can still accelerate. And that's because of the material derivative, capital D by dt of velocity is the acceleration and has a local component, dv by dt, and convective terms, the u dv dx, v dv dy, w dv dz, which are how much the velocity changes by change in position as opposed to how much the velocity changes by change in time. And all flows, at least in this course, are going to obey conservation of mass. All flows do, but in this course, conservation of mass for incompressible flows means that the volumetric strain rate, du by dx plus dv by dy plus dw by dz, is basically 0. There are no appreciable density changes by the pressures that cause fluid flows for the incompressible flows we're considering in this course. All flows also shear. It's one of the defining characteristics of a fluid is that it shears and specifically undergoes a shear strain rate, du by dy plus dv by dx, or any 2 pairs for whichever shear rate you're considering. They shear based upon shear stresses. Fluid flows also spin. They have vorticity. It's 1/2 the curl of the velocity field. It has 3 components as given there. And as a reminder, the difference between shear and vorticity, that negative sign inside the bracket means that it's the 2 sections tending to rotate a fluid parcel rather than tending to close the angle, tending to turn it into a parallelogram. So rotation versus shifting into a parallelogram shape. We're going to use all of these things that we've learned in section 2, where we start talking about the forces on fluid elements. Up until now, this has all been kinematics, considering how the fluid flows, but not why, not the forces involved. The forces involved are going to tie in heavily to the acceleration, but we're going to need to use all of the rest of this as well to understand it. So come on back for section 2.